Thank you, Dr. Pomeroy, for that excellent presentation. Up next, we have Dr. Klaus Wiemer. Dr. Wiemer has extensive experience in many aspects of human clinical embryology, as well as infertility practice management and development. He has over 35 years of experience directing IVF labs and has been off-site director of several fertility clinics. He has published 80 peer-reviewed articles and book chapters in a wide variety of topics in clinical embryology. He is a recipient of numerous awards for his work. His main interest is in embryo culture system, improving laboratory outcomes and studying the effects of follicular stimulation on subsequent oocyte and embryo quality. He is currently conducting research on developing an embryo morphology grading system that can be used to predict ploidy, as well as rate and quality of blastocyst development. He was a founding partner of 2 IVF centers, and he now consults with various IVF centers nationally and internationally, as well as related industries. He also serves as the corporate lab director for Global Premier Fertility, based out of Southern California. He has also received and accepted the role of Head of Clinical Affairs, Americas for Fertility and AI Company. Welcome, Dr. Wiemer.
Wow, thank you so much for being here. This is about the time that Bugs Bunny comes on, so thanks for missing Bugs and Roadrunner. Actually, it's a real honor and pleasure to be with such an esteemed group of scientists. It's a real honor and pleasure. Thank you so much, Nabil and Associates, for the invitation to be here. I'm going to talk a little bit about how AI is applicable. But before we get into that, I kind of want to go back to some basics for a few things and really want to talk about, is developmental history relevant today? We've listened to a lot of lectures over the years that tend to concentrate more on clinical embryology, where we just put the embryos in the incubator, really don't look at them again until day 5 or day 6 or whatever our policies are. And somewhere along the way, we've lost out on the idea that developmental history is important. Back in the old days, we used to collect 1 or 2 follicles at a time based by size. We would then sort our oocytes based on follicle sizes and things like that, because a lot of us felt like, a lot of us came from the animal science industry, and we were very attuned to follicular stimulation, and we really understood all along the way that follicular stimulation consisted of 2 aspects. And so really, whether it's in vivo and normal follicular stimulation or the use of exogenous gonadotropins, really what we find really is there's 2 aspects to cytoplasmic, or to maturation. John Epic very eloquently addressed this back quite a long time ago, and we've got nucleic maturation, which is really the reversing of meiotic arrest, to prophase, it drives meiosis, to metaphase 2. But the real black box is really the cytoplasmic maturation, because it really prepares the oocyte for activation, pre-implantation development. And what we all tend to forget is that this really process is driven at germinal vesicle breakdown. It's initiated by the LH surge, although we know that cytoplasmic accumulation occurs really during the whole, under the influence of estrogen. And so this is a diagram that shows what happens every month or every time period. In mammalian animals, we see that under the influence of estrogen, we have cumulus cells starting to expand, and then soon when we have the LH surge, this causes a cascade of all kinds of enzymatic events. Kinases are released. We have epidermal type growth factors that are released. They are the precursor for all kinds of transcription factors. We even have an inflammatory aspect to this, which causes ovulation. So really, it's a marvel of how many things happen, in a highly synchronized aspect. And this is just every month normal ovulation. So what happens when we layer the follicular stimulation onto this, and this has been something that I've always been interested in, is now we're recruiting secondary follicles that we know there may be some competency issues on. Are these oocytes that were destined to enter some level of atresia, if without the exogenous gonadotropins, are we forcing follicles to develop, and what's the impact of accumulation on all these oocytes? So really, what is the effect of all these exogenous gonadotropins on follicles of varying sizes at different aspects of their development when we start stimulation? And so that's kind of where intuitively my brain has been thinking, is that maybe AI can help us with this, because we really lack an objective way to evaluate the impact of clinical and patient variables, for example, on things such as oocyte quality. We really don't know how to objectively tell a patient up front, are your eggs good or bad? Should you freeze more eggs? Is this a good egg donor or a bad egg donor? And we know that AI now is being used to predict blastocyst development and quality. So really all of this is adding up that we as an industry need additional biomarkers really to help us improve which embryos to transfer, and particularly in the arena now where we're doing so much embryo biopsy. So really, we're at a really neat revolution right now. Those of us that are old enough to have gone from gassing cell culture plates to now working with really sophisticated incubators, and now we're applying AI. And why AI? AI is so applicable to what we do because we have constant measurements and we have outcomes. And so that lends itself very well to large data sets, to deep neural learning. And we have basically two camps that are kind of developing right now, which is really cool. We have those that believe by just looking at an image, we're going to get great information from that. And then we've got those that believe that by looking at how an embryo develops in the incubator, that all of those aspects are going to help us. And I think both platforms are eventually going to work out. It just kind of depends on how your practice is oriented and what kind of questions you need to answer in your clinic. Intuitively, I tend to go more of the time-lapse aspects, only because there's just so much data that's collected from that. So, and also the way I think about time-lapse incubators is not just only they're great incubators. They're like the Maseratis and the Porsches of incubators. They're just built so well. But there's just a huge amount of data and cell cycle data that you can collect. But also the thought is that AI and software can drive all of the information that an incubator collects, can go into an EMR. It can disseminate that information throughout the clinic, also send information to patients and things like that. Excuse me. So it improves transparency within the practice. It helps establish scheduling aspects and things like that. There's a lot of aspects that I think time-lapse AI brings to the picture that I think, and I want to show you some of those as we move on. The other thing too that time-lapse does is it really takes in a huge amount of data. Up to 2.5 billion data points are collected on every embryo, and all of that, it goes into the cloud. And again, because you've got outcomes on all these thousands and thousands of embryos, it makes it very easy to correlate aspects. So one of the first areas that we really pushed hard to try to find ways to work is with oocyte assessment, because this is an area that we really need a lot of work in. And the reason for that, and these are some of the ones that clinicians face all the time, and that is that, how many eggs should a patient be freezing? What does a doctor tell a patient? Like, have I frozen enough eggs? Those patients that are doing social egg freezing. From an IVF perspective, if we look at objective number 2, is patients, often multiple failure patients, need some reassurance that what you're doing might be different. And then internally, as practices, we would love some objective reassurance that our different changes in follicular stimulation might provide this. And then in the donation aspects, both in fresh and frozen clinics that freeze their own eggs, is there an objective way to determine, is this first-time egg donor a good donor, a bad donor? How do we aliquot eggs, to devices when we're freezing them? All these things that we face, and Kim had to face all the time in his egg bank is like, how do I know? Do I put egg number 1 and number 3 together, or 2 and 4 together? Are these all the same quality eggs, or is it just up to randomness? And so hopefully by using AI, we can decrease time to a baby, decrease the amount of money, and create some convenience for that. So the human limitation, though, in really grading oocytes is true. And this is a great paper from the Spanish group that really shows that, okay, these are all the different abnormalities that we've all recognized in the literature. And then, we see in parentheses there about how often it shows up. Really, it's only the smooth endoplasmic reticulums, though, that we found are clinically relevant. All these other eggs and dysmorphic qualities actually lead to blastocysts. So we really kind of suck at grading oocytes. We're not very good at that at all. So this was a project that I worked on a couple of years ago, and this is a wonderful team at with Future Fertility. Was done also with Future Life, a large platform out of Europe. And this was an image base where we were taking images of oocytes prior to ICSI and then putting them into groups. And we could see that, by deep learning, by using this non-invasive oocyte software, we were able to classify oocytes into 4 groups and then culture them. And we found that, yes, AI, by looking at a single image, we were able to successfully predict which oocyte had the best chance. So this is some early work that was done using a kind of a drag and drop image. And so again, here, this showed very successfully that you could image an oocyte and do that. This slide shows kind of a grouping of this. And really, one thing that's important to know is right now, all the oocyte AI work, even if it's done in a time-lapse incubator, is based on a single image. So, but some images are done pre-ICSI, some are done post. So the slide on the left, which shows the Chloe OQ scores, those are the fertility oocyte scores. These are scores that are based on pre and post ICSI, because we're actually finding that if you image the oocyte before ICSI and then image the oocyte after ICSI, that the combination of that data increases the area under the curve. But the slide, the results on the other parts of the slide really show again very successfully that there's multiple approaches to using AI, and that AI can successfully grade oocytes, can successfully predict which ones are going to become blastocysts. So now we've got an emerging set of tools that are helpful. And then what about how does this apply though across large platforms? And what's interesting though, and this shows you really early on that this is an infancy of a field, because we find areas under the curve ranging from 0.6, which is barely better than flipping a coin, all the way to 0.7. And overall, we see that the area under the curve is really only 0.6 in this. And so we see that these are areas that we still need to improve on, that as we collect more data, we can find. But nonetheless, when we group oocytes into bins, as we're called, we can find that we can successfully start to do this. So now we're starting to see results where AI can help in oocyte grading and will provide us lots of different tools. So what about applying AI to embryo grading? Again, great, done here by Jonathan Hall's group. We can see that the Life Whisper program works really, really well. And what they did in this study is they were comparing various different categories. They used the EVA system. They were also comparing the Gardner system and then their Life Whisper AI support. And you can see in the bar graph down below that their area sensitivity and specificity were their AI platform, which is worked really, really well. And so that worked out great. This says 8 minutes. That says 5. I've been going off of that. Uh-oh, I better hurry up. Us Southerners don't talk that fast, So what about time lapse? And how can that help us in our clinic today? And really, as we're facing the shortage of embryologists, one of the things I like a lot about time lapse is that now we can come into scheduling this. So for example, as early as day 3, we can start to predict, how many embryos are going to become blastocysts, and we can also predict, which embryos to transfer. And so again, I'm going to challenge the group that we may be overusing embryo biopsy, and perhaps by using AI to help us know which is our best platform, we can start to do more fresh transfers. And then also, we can also use embryo development to help us a little bit with which embryos for biopsies and stuff like that. And so different applications of how time-lapse can be used. It can be used from egg freezing, as we've talked about, to determining blastulation on day 3. determining how many blastocysts per patient we're going to get. Again, I mentioned ploidy and implantation. If you look at the graph on the far right there, this is recent data from Kathy Miller's practice. We found that when we looking at euploid embryos and we used embryo development, that we had beta improvements. So that leads me to this next aspect, which is really like, what is the effect of developmental history on ploidy? And why is this important? Well, a lot of people have mentioned this, in that not all euploid embryos are created equally. And then here's many of the reasons why euploid embryos may fail to implant, from mitotic errors to metabolic issues to cytoplasmic anomalies, insufficient resources in the cytoplasm that are accumulated during follicular stimulation, errors in genetic imprinting in various areas. So there's a host of aspects that are going to impact potentially why euploid embryos that are high quality, morphologically looking, don't implant. And so here's some work from Kathy Miller's practice. I'm going to skip over here. And what this data shows is that embryos really that are all euploid can divide within a fairly large range. The data in the orange shows those euploid embryos that failed to implant. The ones in this darker green were outside. In other words, those embryos implanted, but they didn't make a baby. And then that very narrow light green, those are actually the embryos that result in live birth. And when we looked at the morphokinetics of those embryos, you can see, for example, time to start to blastulation to end of cavitation, time from 4-cell to 8-cell. All these variables were significantly different in those embryos that resulted in a live birth. I apologize for the bar graph being slightly off. But again, we're starting to see that there was some room for error. And this makes sense because nucleic maturation and cytoplasmic maturation are somewhat independent events of each other. And so when we looked at her outcomes by scores, we saw that, you had a 72% live birth rate for embryos where AI predicted a high score. In other words, the embryo met or exceeded all of its benchmarks, compared to 48% for euploid embryos that still had a good morphological appearance, but these embryos, either had some kind of erratic aspect in their morphological history during their development in the lab. So really, again here, this is just some more data that indicates that it can be replicated in other centers. This is from Harley Street in Europe, in Great Britain specifically. And again, you can see that in their group, they also found this again. So there is mounting evidence that shows that morphological embryos, there's a wide range that's tolerated for euploid embryos, but that the ones that actually result in an ongoing pregnancy rate, that morphokinetics is much lower. So final thoughts. What are the effects of follicular stimulation on cytoplasmic contributions to overall embryo health? Is a time-lapse approach a way to look at all this? Can AI can successfully be used to degrade oocytes? Time-lapse and morphokinetics can pick up subtle characteristics. Data indicates a rate of blastocyst development might be an indirect measurement of cytoplasmic health. Certainly that's the data that we're looking at. And I do think that taking developmental history into account when we thaw embryos helps out a lot. Thank you so much for all your time.